Hello again. Let's talk about the next chapter. So we are starting quantities and chemical equations. Now, this one covers a lot, but it's not going to seem very long. So it's kind of a change. We are switching from the visual to the mathematical. So basically the qualitative to the quantitative. So we are going to cover chemical quantities. We're going to talk about something called empirical and molecular formulas, chemical equations and stoichiometry, limiting reagents, theoretical yields, and percent yields, concentrations, and then there's something called quantitative analysis. And yes, there are 3 handouts for this. So I tried to separate the topics out. So each handout isn't very long, but it each covers a different topic. All right, let's start with the basics. Chemical quantities, okay? We're going to start number crunching. And the first chemical quantity is either called the molecular weight or the formula weight. Now, technically, a molecular weight only belongs to a molecule, where a formula weight pretty much belongs to any kind of a formula. And again, in Chem 111, that's kind of a nitpicky thing. I tend to always just say molecular weight, whether it's ionic or molecular, but technically that is incorrect. But formula weight works for everybody. All right, so what is the formula weight or the molecular weight? Well, it's how much each of the atoms weighs. And we can talk about one atom, okay, which is AMUs, or we could talk about overall a whole bunch of them, and we could say grams. I'm going to go over to the whiteboard. Oh, it's still on the whiteboard. All right. So if we are talking about mass, and again, the term mass and weight, they actually don't mean the same thing. But since we're pretty much constant here, on Earth for what we consider, I use them interchangeably. But a physicist would not, okay, because mass is independent and weight is dependent on the gravitational force. All right, so we're going to talk about the mass and we're going to talk about water. All right, so we know that one water has 2 hydrogens and 1 oxygen. Well, I also know that I can have a molecule of it, or I could have more of it. So one molecule contains 2 hydrogen atoms and 1 oxygen atom, right? So there's only one of them. If that's true, I'm going to use something called AMU. It's the atomic mass unit. Where did that come from? Well, we took a sample of carbon-12 and we used it as our reference point. And we divided it by 12. So in comparison to carbon-12, one atomic mass unit is a 12th of that. And that's what is assigned to all of the elements on the periodic table. So if you're looking at your periodic table, hydrogen is technically 1. But remember, that is a weighted average of all the common isotopes. So you're never going to get just the number 1. You're going to get, some kind of a ratio. So if it's over 1, that means some of the isotopes must have been over 1. But again, it depends on how many there are. All right, so if we're talking about one of them, we're going to call it atomic mass unit. And we're going to get the numbers off the periodic table. So I have 2 hydrogens. I have 1 oxygen. And on the periodic table, the hydrogens take as many significant figures as you need. If your calculation needs 3, I suggest you have to take 3, maybe 4, right? So 1.01, and then 1 oxygen is 15.99, which is commonly rounded up to 16. So this is 2.02 plus 15.99, 18.01 AMUs. So if I was only talking about one molecule of water, it would weigh 18.01 AMUs. Well, the same could be said of an ionic compound. Let's do magnesium chloride. We technically wouldn't call it a molecular weight, we'd call it a formula weight. But if I'm only talking about one, Now remember, ionic compounds are held together by pluses and minuses. So the reason you go down to the smallest ratio is so that you can tell me what the smallest ratio's weight is. All right, so magnesium, we're looking on the periodic table. So I have one magnesium, I have two chlorines. So one magnesium is, pulling out my reference sheet. All right, one magnesium is 24.305. And again, do you have to use all those numbers? Don't use as many as you need. I need two chlorines, which is 35.45. And so, with my calculator, this is 70.90. And notice I limited myself, so I don't actually get to keep that one. And so those added together are 95.21. Am I talking about just the smallest ratio of one formula, or am I talking about a molecule? I'm just talking about one, so I'm going to put A and U. All right, well, that's not very useful because in the lab, I can never measure out just one of them. So I'm going to have to come up with a reference that tells me how many I'm measuring. And that is called the mole. The mole is the chemist's dozen. So if I said 12, your brain could interpret that as dozen. Or if I said dozen, your brain could interpret that as 12, except Baker's dozen, but we're not talking about that. All right, so for our mole, we're going to set an amount. Now, are we going to arbitrarily set this amount? No, there's experimentation and some theory in there. But 1 mole is equal to 6.022 times 10 to the 23rd. And yes, that's on your reference sheet. Things. Now, why in the world do I say things? Well, because I can change how many things. Can I have a mole of donuts? Yes. Can I have a mole of pennies? Can I have a mole of books? Okay. It just means 6.022 times 10 to the 23rd. That is also called Avogadro's number. And it's given the capital or the symbol capital M, small capital A. So those mean the same thing. All right, well, how does this work? This is trying to tell us that we're going to have a set relationship. 1 mole, regardless of what it is going to contain 6.022 times 10 to the 23rd things. Will it have a different weight? Yes. Will it have a different volume? Yes. Okay, I'm just saying I'm counting them. So if I had, oh, I don't know, a mole of feathers and a mole of gold atoms, would I have the same number of things? Yes, but they would take up very different volumes and they would take up very different weights, very different weights. So we're going to play with this idea of mole back to water. All right, if one water was 18.01 AMUs, well, how much would 1 mole of water weigh? And then we would just change the unit to 18.01, and then you would have to put grams per mole because there isn't just one of them. So you're telling me my relationship. And so the molecular weight is 18.01 excuse me, grams per 1 mole. And so we are going to use the periodic table to determine all of the molecular weights and the formula weights. It is your ultimate cheat sheet. It's your ultimate friend. Let's try another one. You know what? Let's do iron nitrate. So this one happens to be iron 2 nitrate. What is the formula weight? Now, the reason I said formula weight is technically it's ionic. All right, so I'm looking on the periodic table and there was one iron and my iron weighs 55.85. One iron. And remember, this is for the whole thing. So there's two nitrogens. So 2 times 14.01. And there's 6 oxygens. And I'm just going to round up to 16.0. That is the total weight of iron nitrate. Let's add it up there. Check myself, 124.02. All right, now I could say AMU if there was just one of them. Or I can say 124.02 grams for every 1 mole. I could also say 124.02 grams per 6.022 times 10 to the 23rd molecules or things right there. Okay, this is just a tool. So go back to dimensional analysis. Having the mole calculation for the molecular weight or the formula weight is just a tool. Just a tool. All right, go back to the notes. Whoops, that's not what I was going to do. Okay, so we have this term molecular weight and formula weight. We just introduced this thing called the mole. It's the given quantity. And yes, you can drop the E off. Ooh, we give you such a shortcut. All right, so you have a weight. So if it's one atom, it would be called atomic weight. If it's one molecule, it would be called molecular weight. If it's one ionic compound, you would call it formula weight. And you would add those up off the periodic table. And then you just need to decide this quantity or the relationship. And again, one probably isn't very unique. So we use the mole. So Avogadro's number. And what does it always reference to? The number of carbons in carbon 12, in 12 grams of carbon 12. And then I just did basically what I did on the whiteboard right there for you. And notice it's all about the words. It's all about the words. Sodium chloride, well, what's inside sodium chloride? Ions of chloride, ions of sodium. In 1 mole, I haven't broken it down yet, so I have formula units. In 1 water, okay, individuals are molecules, but if you break it down further, it's atoms. And so that's the difference between them. All right, that takes care of molecular weights. Let's do just this little blurby here at the bottom before we go on to our next topic. Mass per percent is nothing tricky. It literally is a percent. So mass of what you're interested in divided the mass of the whole. All right, now, why is that very useful? Well, it depends on the situation. So for instance, oh, this one's still on the board, so let's use it. What percent is iron inside of this iron 2 nitrate? Now the key is what kind of percent do you want? You actually have to be told because it's not part of the definition. And so do you want mass percent? Do you want atom percent? So generically, if I wanted atom percent, there's 1 atom of iron in, what's that to me? 1, 2, 3. So there's 2 of those. There's 6 of those. There's 1 of those. So 6, 7, 8, 9. All right, but I already knew that. Okay, I already know the formula. So usually when you see percent, it's always called mass percent, and I'm talking about the actual weights. So this one's not so useful. But how about the mass percent? Well, I know the iron weighs 55.85. And the total weighs 124.02, convert it to a percent. And the percent of iron in iron 2 nitrate is 45%. So let me see, and I get 4 sig figs, 45.03%. So when you see mass percent, that's all it's doing. It's just converting the weights into, oh, well, could you also figure out the oxygens and the nitrogens? Yes, either subtract from 100 or just put their number up on. All right, that takes care of the basic introduction to quantities. And until next time, Dolly out.